All right, so yeah, as I said, this is our last session of technical talks, but please make sure to stay online after this because Aaron will be wrapping up with the Swiss contest and other stuff. Our first speaker is Zhang Chunyu, who's joining us from China. It's close to 4:30 in the morning there, so we appreciate that he's able to join us, and he'll be talking about elasticity problems. So take it away, Zhang.
Okay. Thank you for organizing the workshop. So good afternoon to you, but good morning to my colleagues. So I'm happy to share some of my recent work on modeling the complex deformation of elastic media, but with consideration of high-order macroscopic deformations. So my name is Zhang Chunyu, and I'm from Sanyang University of China. As you all know, the classical solid mechanics has seen a great success since Cauchy introduced the concepts of stress and strain. So with the advent of computers, people can solve the Garnier equations using the finite element method. And running analysis has become a routine. However, it's interesting to note that many seemingly simple problems are not yet resolved. For example, we all know that the stress and the strain get singular around the crack tips. But in reality, it's not true because any material has resistance to geometry defects. Another case is that in the textbook, we know that around the circular hole of a plate, the stress and the strain concentration factor is a constant of 3. Again, in reality, it's not true. When the hole gets smaller, the strain concentration gets smaller too. So if the hole gets small enough, the stress and the strain concentration will disappear. The third case is that if people use the inundation test to measure the mechanical parameters, for example, the Young's modulus or the hardness, so the extracted values is not a constant either. So the value will decrease with increasing the unit taps. So the problems are rooted in the deficiency of the classical definition of stress and strain. To improve the framework, so many high-order theories have been proposed. For example, the strain gradient theory, where the strain gradient, the strain energy density, is defined by introducing some high-order terms. Usually, they are expressed by quadratic terms. But for this theory, multiple length scales L1, L2 have been introduced, and also the question arises that whether it is correct for the improved strain energy density. Another very famous high-order deformation theory is proposed by Aragon, that is the non-local theory, which assumes the stress of a point depends not only the strain of that point, it also depends on the strain in the neighborhood. So again, the problem is why. So what's the source of this non-local interaction? Recently, another theory that is the macromorphic theory also proposed to unify the high-order deformation theories. But the problem is people have to choose empirically the parameter, for example, the L1, L2, to describe the softening behavior. Maybe the positive sign has to be chosen to describe the hardening behavior of a minus symbol is chosen. So what's the reason? Why? So for conclusion, the high-order theories can resolve some problems. For example, to remove the singularity of stress and strain around the crack tip. There's still some problems. For example, the sources of the high-order terms are unclear, and also have to introduce several length scale parameters. The last difficulty is that in these high-order theories, the boundary conditions contain some high-order terms which impose great difficulties for imposing these boundary conditions. So we propose a new theory, and before we introduce the new theory, let's analyze the conventional process for modeling the continuum. For any real material, it is a multi-skewed and inhomogeneous system. To use the integral or differential mathematical operators to model the complex system, we have to impose a homogenization to get an ideal continuum. So that means that we need to make a homogenization over a small region, which is called a representative volume cell, a volume element, short for RVE. So within the RVE, we perform an average not only on the material. For example, we define average the modulus, average the strength. More importantly, we have to make an average over the physical fields. For example, the strain, the displacement, and so on. So in the classical framework of continuum, we keep the average term and neglect the high order terms. But recently, we found that the homogenization error, is also very important. Suppose the strain field is distributed in a nonlinear form within the RVE. So the averaged behavior, of course, is not the averaged behavior, the true behavior. Then we call this as a homogenization error and define it as the averaged value to the representative value as the center of the RVE. By using the Taylor expansion, we can alleviate this homogenization error. For example, we can expand the scalar field, for example, U is a second order expansion and make an average over the RVE, and we can see the high order terms, the Laplacian, the first order Laplacian, the second order Laplacian will appear in the average value. So that means that if the physical field takes a nonlinear distribution within the RVE, the error should be considered in an appropriate way. By using this form, there's an advantage that we only need only one scale parameter, no matter how many terms you choose to keep in the homogenization field. Now I move to the problem of mechanics. By following the idea, we can expand the strain energy density by including the higher terms. Here we can see that if the strain is nonlinearly distributed within the RVE, the strain energy density composes of two terms. One is the conventional term, which here lambda and mu are the Laplace constants. The most important that we have to consider the high order strain energy terms. So it's much more complicated than the conventional strain gradient theory, because we can check that besides the correct terms, there are also some cross terms. These cross terms, for example, here, this one and this one, this one. These cross terms may be negative or positive. If it is a positive value, that means the new strain energy density will be greater than the conventional one. The material will behave in a hardening way. Otherwise, if the cross term is negative, so the strain energy density will be less than the conventional counterpart, and the material behaves in a softening way. So once we have this strain energy density, we can compute we can define the total potential energy of the structure. Thus, we can apply the principle of minimal principal potential energy and solve the structural deformation. So, but we have to consider the higher order terms in the total potential energy function. If we expand this functional, it's much complicated, but it only considers the first order and the second order gradients. So it's a little bit challenging for numerical solution because we have to consider the high order gradients. Here we have to consider the three order gradients of the displacement. And we have to use high order finite element method, high order finite element. So we choose M5 to do the computation. And to simplify the computation, we define the string as a supplementary variable in addition to the major variable that is the displacement. Thus we can solve the displacement and the string simultaneously. By using this way, we can keep the gradient no more than 2. Final energy functional can be constructed by using the augmented Lagrange method. Here, this is the constraint that we define the epsilon, the string as a supplementary variable, the gradient of the displacement, and apply this constraint by using the augmented Lagrange method. Here, this is a Lagrangian term, and this is the penalty term. This method is the advantage is that the penalty parameter is not necessary to set in this parameter to be a large value. We can choose to be a moderate value. And then by using the variational method, we can decompose, we can solve this equation as 3 coupling equations. The unknowns are the displacement, the string, and the Lagrangian multiplier. To solve this equation, we developed the solver called the curvature-correct finite element method within the framework of M5. We redefine and supplement the several methods to these classes, mostly related to the computation of the Hessian matrix. And we define several bilinear form integrators to compute this submatrix for the coupling. And, so now let's show the performance of the theory and the code by introducing several cases. The first is the hardening behavior of a macro cantilever beam. This is a material is a copper, and this is a very thin, very small beam. And many experiments have shown that with decreasing the thickness of the beam, the equivalent bending modulus will increase. So we model this and choose the parameter to be the length parameter to be 2 micrometer. Now we can compute the bending deformation and compute equivalent modulus. It's interesting to note that the method and the code can quantitatively reproduce this dependence of the modulus with the thickness of the copper beam. So maybe it's interesting to analyze the result from the prospective energy. So although the classical theory of beam give us the string is linearly distributed within the beam, but in fact we can see that on the right figure we can see that some high order energy density appears. So especially when we decrease the thickness, the fraction of the high order free energy will increase. Thus, generally the beam will behave in a hardening way. So that can explain why the equivalent bending modulus will increase, increasing the thickness of the plate. Okay, the second case is the circular hole. So the textbook tells us the concentration factor under uniaxial loading is 3, but in fact it's not. To check the question, we did a measurement of the hole around the hole by using the digital image correlation. We started 2 types of defects: the circular type holes and rounded square holes, and measure the strain around the holes. So ABACS predicts the strain, and the CCFEM predicts the strain also. We can see that ABACS predicts the strain in a very concentrated way, but the DNC experiment shows that the strain is not that concentrated. It's smeared. So this is because the high order strain energy come to action. And also the CCFEM can give a much reasonable prediction to the strain. Besides the strain, we also compare the fracture, the fracture strength. We record the strength, the stress concentration factor, and compare with the predictions. You can see that for both the circular holes and the rounded square holes, predict the stress concentration factor are pretty good, in good agreement with the experiment. And for all the experiments, for all the computations, we use the same set of parameters. That means we don't need to collaborate the scale parameter case by case. For all the results, the parameter for 0.85 millimeter is used. And they also can be analyzed from the energy perspective, because we are decreasing the holes, more energy, more higher fraction of higher order strain energy will come into play and contribute to the total strain energy density. So the material will become in a hardening way. The last case is the softening in thin test. So experiments also observe that by increasing the initial depth, the expected modulus will decrease. So for metals, people attribute the softening to geometrically necessary dislocation. But for elastic material, for rubber, a similar phenomenon is also observed. So we studied the problem by building a simple model, because we cannot analyze the contact yet. So we build the equivalent model by applying equivalent pressure and changing the contact radius A. So we can see that the modulus, the high order strain energy is negative for this case because of the distribution is different, and the total strain energy density is less than the conventional strain energy density. So this can explain why the extraction modulus will decrease. So next, we hope to make an interface with the treble, which will be presented in the next slide, in the next presentation. So to run a complete contact modeling. So as a conclusion, we develop a new solver based on the homogenized energy theory, and this theory seems can explain many seemingly interesting typical problems, and we implement the theory within the FMEM framework together with the augmented Lagrange method. And we are now extend the solver to model the brittle fracture. And hopefully in the future, we hope can to solve these elastomer plastic problems, for example, by considering the complex deformation of the plastic dissipation. Okay, thank you very much for organizing the workshop.
Thanks, Dan, for sharing your work on this homogenized energy theory. I think we have time for one quick question.
Yes, may I ask a question?
Sure.
Sure.
Yeah. Hi, Professor Zhang. It's really interesting talk. I just have one question about the H parameter introduced. Does it have a physical meaning, or is a fitting parameter?
In fact, H means the size of the homogenization region. It is related to the microstructure. In fact, we can measure the parameter here. So when we perform the homogenization operation, we need to find the region of RVE. So H means the size of the RVE. So we can measure this parameter, for example, by analyzing, by conducting correlation analysis of the microstructure. In fact, this parameter is the correlation length scale. So we did several experiments, for example, using the different shapes of holes, and make sure that one parameter is enough to predict all the different shapes of defects. So it's possible, it's very likely that this parameter is a material parameter independent of loading conditions.
I see. That's great. Yeah, thank you.
Thank you.